consider for quite a while the effect of diffusion on mass transfer. Now, diffusion is basically a zero driving force effect. Really don't have to have a driving force for diffusion to occur. You can think of the diffusional effect as if you had a drunk coming out of a bar. That's a Mose, and he's so drunk that he can only stagger one way or the next on the sidewalk. And he can staggers one step, and then he staggers back, and staggers forth, staggers back. Now, the position of that drunk after some period of time is going to be a statistical occurrence. The drunk may be some distance down the street, he may be back at the bar entrance, or he may be some distance down the other way in the street. The basic description of that sort of thing is what they call a random walk. And you can have random walks in 1, 2, 3, or as many dimensions as you care to have it. But what we can do is use binomial statistics to calculate where something is going to be after some amount of random walks. Well, we won't do the derivation, but the point is that if we think of this as time 0, 1, 2, 3, 4, and so on, and our drunk can only take steps of a certain length, we can lay out a little grid. And you see at time 0, our drunk is at the bar entrance, and he could have possibly walked one step over, and this again is time, so he could be over there, or he could have gone this way. Time 2, he could have gone to here, or here, or here. So you can see there's kind of a network being developed. Time 3, he could be at various points along this axis. And the point is that at some point he's going to be somewhere around the mean, but he could be distributed anywhere along that probability. And effectively, what you see if you do this process long enough, you just see a Gaussian distribution of states. And this is what happens, for example, if we take some concentration of some solution and we drop it into a bucket of water, and if we just allow diffusion to occur, that spread will be a Gaussian type distribution. In that case, it would be a three-dimensional Gaussian distribution. Well, we can draw that mathematically. We can say the average displacement, this mean square deviation from 0, is related to the length of the step, the time between steps, and the total time of the system. So this is the mean square displacement. And so our drunk may take a step that's 1 yard or so. He may take a step every second. A molecule in solution may move on the order of a microsecond or nanosecond and move only a few angstroms or a few nanometers. And so the tau, length of step, or the time per step. So that would be an experiment that's kind of discrete. We can actually rewrite the equation in terms of the diffusion coefficient, where the diffusion coefficient incorporates the length and the time per step, and that's a constant for a particular species, and it usually has units of centimeters squared per second. For a molecule in aqueous solution, we typically see diffusion coefficients from 10 to the minus 5 to 10 to the minus 6 for small molecules. You get the molecules that are bigger, 500 and so molecular weight, we might get to 10 to the minus 7th. And of course, the concentration, as the viscosity of the solution changes, the diffusion coefficient changes as well. All right. And D is related to sort of the mean free path. And as I said, these are the relationships to it. I just want to show you on the computer how easy it is to calculate something like this. You can see here a random walk simulation where I show the displacement versus time. I get a lot of points, so this computer is a little slow. But you can see there's two lines which should be the average displacement either in a positive or negative direction. And each of those set of points is a different set. And if we can recalculate it, I think. There we go. And you can see now that the distribution of points has changed. But each one would be some time. And you can see some points are far out on the graph, and some points are closer to the graph and to the middle, and some are close to zero displacement, as you'd expect. So there's like 50 different traces on it. And I put that on the web page if you want to play with that a little bit. You can see what happens. There's no telling where that particle is going to be. It can be a maximum distance away depending on the number of steps you take, but it can be anywhere within that envelope. But it will most likely be on average on this, around this line. Okay. So for our electrochemical experiment, we can think about our average displacement as being equal to the square root of 2 dt, which means that we can think about times and diffusion events. So if we give our molecule 1 second to diffuse, we can calculate our average displacement as about 1.4 times 10 to the minus 3, assuming d is equal to 10 to the minus 6 centimeters squared per second. And that's about 14 micrometers. If our time is 100 seconds, or 1.4 times 10 to the minus 2, or 140 micrometers away. So because of the square root dependence, it takes quite a long time actually to see a significant movement. If we go to a 1 millisecond time scale, now we're down to 1.4 times 10 to the minus 4 centimeters, or approximately 1.4 microns. So that's one I kind of like to remember, is a millisecond is about a micron. Giving yourself a millisecond in an experiment is about a micron's worth of diffusion. So if you don't want your molecule to diffuse very far, you have to do your experiment in a very short period of time. Okay. Well, this diffusional process can be modeled by two important equations, and these are the two equations that we're going to be interested in. The first one is called Fick's first law of diffusion. And it says that the current divided by the charge in the area is equal to the flux of species J along some axis x at some time t is equal to minus d, and the gradient of the concentration of species J oops, dx, not dt, sorry, dx. So the flux of species J is, that's given for diffusion, is going to be related to the concentration gradient of species J. The sharper that concentration gradient is, the higher the flux rate will be, and it will be also dependent on the value of the diffusion coefficient. And we can think about why diffusion really doesn't require any activation. It doesn't require any energy. It's just a simple statistical distribution. Suppose we have a set of boxes that contain solution that have imaginary boundaries. Well, if we put in species J in that box at the start, because of the random motion of the molecules, some of those molecules will find themselves, after some period of time, in species in the next box over. So there will be some flux of species J in the next box. Let's see if we can draw this a little bit so I can write it. Draw these boxes bigger. So J, the species J, the flux of J going into the next box, and then the flux of species J that's modified somewhat, going to be x plus delta x t, and so on. And so we're going to move in each of those boxes. Now there's always some fraction will find itself in an empty box, and some, of course, will diffuse back into the original boxes, but there's always going to be some movement along that axis to fill up all those boxes. So eventually that concentration gradient will force all the boxes to have an equal amount of J in it if we allow diffusion to occur on a long time scale. So that's the first law of diffusion that will help us to solve these things. What about the second law? And this second law gives us the change in concentration with time. So the change in concentration with time is equal to the diffusion coefficient of species J times the second derivative of the concentration of J with respect to x. All right, so both of these that I've written are for fixed first law, and second law are for one-dimensional diffusion down a one-dimension gradient. Obviously, in most situations, we're going to have more than one dimension of diffusional process. It can have many dimensions, like 3 dimensions is possible. So generally, we can write, say for fixed second law, we can write engineering students will probably be more familiar with this, a grad function, which is just a generalized function that we can substitute any sort of transformation that we like. So the grad function for a spherical diffusion rather than one-dimensional diffusion would be equal to the second derivative with respect to r, or rewriting our fixed second law for spherical coordinates rather than one-dimensional coordinates, one-dimensional linear coordinates, would be just like so. Okay, and that's a little bit more complicated than the equation for in one dimension. You've got a similar term here and here for the two, but you see that this part of the expression for spherical coordinates, I should write that there, spherical coordinate, is different. What's the difference? Well, in a one-dimensional problem, we can consider that the area of our electrode never changes. The amount of solution available to feed a one-dimensional electrode is always the same. Whereas for a sphere, what happens is that because diffusion is allowed to occur in 3 dimensions in the sphere, the volume of solution that diffusion is occurring in is constantly growing. So at short times, the volume of solution affected by diffusion is quite small, but at long times, that amount grows and grows, and so that term here is this second part of the term here that is relating that expression, the area change. All right.